Batman Unlimited. One of our viewers noticed that I was able to load G-code onto the Fidel CNC machine directly off of a network attached storage, and they inquired more information on how that's actually done. So in this video I'm going to detail the system that I set up that allows me to access network attached storage directly from the machine. Originally these machines have a simple RS-232 port on them, and you would use a little bit of PC software to then download code onto the machine. That was a little bit cumbersome. You have to go to the machine, or you have to go to the PC, open your G-code file, load it into their software, then go to the machine, put it in tape input mode, go back to the PC, send the file, go back to the machine, go back to the PC. It was a very time-consuming and a bit arduous task that really didn't need to be that complex. With a little bit of experimentation and reading through the documentation, I was able to run the machine through the RS-232 port. So I put an embedded device inside the machine cabinet that also connects to my network that has access to the network attached storage. For my day job, I'm actually a systems architect. I do a lot of work with National Instruments products and National Instruments LabVIEW. So that's the product line that I chose to use. We had an older style CompactRIO laying around that wasn't being used anymore, so I repurposed it for this. I'll show you what one of these CompactRIOs look like up close and kind of describe how they work internally. So this is an example of the CompactRIO that's inside the machine. The one in the machine is a little bit older. What this has is it has a embedded floating point processor that runs a real-time OS in this section of it, and then on this back plane there's a FPGA, field programmable gate array. The embedded processor has embedded Ethernet, RS-232, USB, some of them have some SD cards, they have different options. The FPGA is typically used to interface with modules that plug into these slots. So this device will typically be used with analog input, analog output, digital I/O, communications protocols to perform some type of task in industry, manufacturing, or aerospace. You don't need to use a CompactRIO for this application. I just happen to have one laying around. So that's what's actually inside the machine. I'll show you in a minute how I installed it in the machine. This task can really be performed by any embedded real-time operating system. The Arduinos or Raspberry Pi should be able to do this application as well. I just chose CompactRIO because we had one laying around that wasn't being used, and I'm very good at LabVIEW, so I was able to whip this together within a couple of hours and have it up and running. So the high-level view of how this works is the CompactRIO is interfaced to the machine through RS-232. It can receive data from the machine and interpret it, and when the CompactRIO is triggered for a command, it then can take control of the machine and then perform functions on the machine as you would type them in on the keyboard. In addition, it's also connected to our network so that it has access to anything on our network. So it acts as a bridge between the network and the Fidel CNC. Let's take a look at the actual hardware installation in the back of the machine cabinet. We're in the back of the machine electrical control cabinet. So there's our CompactRIO in the bottom of the cabinet. We have an Ethernet connection coming in through the back of the cabinet. That leads to our network. Then there is a RS-232 connection that goes into the cable, and then that cable follows the bottom here and then comes up into that connector on the far left, that blue one, in the center of the frame. And that is the connector to the CN controller. The other thing that we added to the C-Rio is there's just a small USB thumb drive there, and that is used for local storage of any G-code files that we want to download in DNC to the machine. The C-Rio runs off of DC power. It's got a 9 to I think 36 or 39 volt range. So we have a 12 volt DC supply. We wired it right into there. we're at the machine console. I don't have any better way to do this other than just videograph the monitor. You'll have to bear with me here. So right now the machine is idle and it's in its manual command mode, so it's waiting for you to type in a command. Normally you could type in like TA, 1, which would be tape input, and then you could use PC software to send the file over to the machine. With the CompactRIO installed, the CompactRIO can intercept and interpret everything that you type in on the machine's keyboard. So the first thing that we have to do is tell the machine to change device. So that's a CD enter. What that does inside the machine is it now starts to echo everything that I type in on the keyboard out that RS-232 port. The CompactRIO will then receive all of that serial traffic and it starts scanning it for commands, and then I used the plus sign to execute the command. It was just a character I used. It was convenient. It was right under the enter key. If I want the CompactRIO to do something, what I have to do is type in a command that the CompactRIO recognizes. So I have a help command. So HELP. So what just happened is as I typed HELP, it also got sent out the RS-232 port. The CompactRIO received it and is holding it in a buffer waiting to do more action on it. So now if I want to execute that command inside the CompactRIO, rather than hitting enter, which would have the machine execute it, I hit plus. By hitting plus, that triggers the CompactRIO to say, oh, he's talking to me. He wants me to do something. That string that was typed in then gets passed to the command interpreter, and then the CompactRIO will take the appropriate action. In this case, that action is to list all the commands that are currently supported by the CompactRIO. To do that, the CompactRIO just starts sending serial information through the RS-232 port to the machine. When it does this, though, it takes control of the machine. While it's doing that, the keyboard on the machine console no longer will function. That's why you see this by after every command. At the end of the function for the CompactRIO, it sends a terminate command to the machine to return the control of the machine back to the console keyboard. The unfortunate side effect of that is every time we do a command, we have to keep doing CD. So another command that we have is dir. So that's the command I use to change folders. So I have a test folder in the master CNC directory that stores all my G code. So if we do a dir test, now it just changed our folder from the root of CNC jobs on our network location to tests. Now if you notice, what I typed in was TEST, not TESTS. A feature I did that I thought was pretty neat, these keyboards are kind of a pain in the butt to type on. So as long as you type in enough characters to where what you type in is unique among all the file names or directory names in that current folder, it will select the unique one no matter what the rest of the name is and then change it to that. So then you can see what it changed it to. So now that we changed our directory path, other directories I have are based on job number, so each job has its own folder, so I can easily browse to all my different jobs. Now we need to actually load a file. So I have a file command. Oh. Need to do the CD. So file, and then I have a linear test. L-I-N-E-A-R test. Now what the CompactRIO just did is it took my command of I want to open a file that's called linear test. It went out to the network attached storage in this folder and looked for a file called linear test. It found it. It then copied the file from the network attached storage down onto the USB drive that's local to the CompactRIO, and then it just displayed the first couple of lines in that file so you know what you're looking at. Once the file is local inside the CompactRIO, now we have two choices. We can either A, tell it to download it into the machine memory, or B, we can drip feed it to the machine and run it through DNC. This machine is very limited on memory. It only has 44K of RAM. It cannot hold very big files. So as soon as you start doing interpolated toolpaths and adaptive clearing strategies, this machine just cannot do it from internal memory. But with the CompactRIO using DNC, we can stream a file that's almost endlessly large. We've got a couple of gig storage thumb drive on there. As long as the file can fit on the thumb drive, the CompactRIO will just keep streaming the file all day long. The biggest file I think I've run so far was like 4 megs, which is a huge G-code file. Let me show you how we download this file. So with the machine language, to send a file to it, you have to tell the machine a TA,1. And what that represents is it's actually called tape input. When this machine was made, the way that they used to store files were literally on like these cassette tapes. And there was a language where the cassette tape talked RS-232, and the machine could start and stop the cassette tape as you program the file. So that's where this TA,1 stuff comes from. What I did in the CompactRIO is I told the CompactRIO to be able to interpret the same command as the CNC machine. So we'll do a CD, a TA,1, and then instead of enter, we'll hit plus. Now what the CompactRIO will do is it will take that previously specified file, put the machine into input mode, and then send the file to the machine. So you'll see all the files scroll by on the machine. This file is just a linear interpolation of a circle. It's a test file I wrote to quantify that my DNC program is working. So I ran this a couple hundred times overnight and came back out and made sure that the machine was still at 000. It's run in incremental mode, so if I missed any of the DNC messages, it would have not finished at 0 anymore. So now the file is loaded into the machine. We can do a PA, which is a program edit basically, and you can see that file in the machine. So this is internal to the machine memory. We can then, if we wanted to, we could do an auto. There's our test. We could hit start. And now it's running that file. And it's happy as a clam, cranking through. I'll let this file finish out. It just takes a couple of seconds to run. Now if this file is too large to fit in the machine memory, now we have to use what they call DNC. DNC is just a protocol to allow you to send G-code lines in real time from a computer, or in this case an embedded processor, to the machine, and the machine will act on it. Now the machine has an internal buffer, so you can send a couple of commands ahead of time, and then once you send those couple of commands ahead of time, it will keep that buffer full, and then as the machine execute commands, it will request more information from the PC, or in this case the CompactRIO. So now our test was done within the machine. So let's show an example of DNC. So we'll go back into manual mode. To DNC it, there's actually 2 DNC protocols with a Fidel machine. One of them is called DNC, and then the other one is called DNC X. DNC X stands for X modem. X modem is an old protocol that used to be used back in the dial-up days to packetize information with a block counter and a checksum. By using DNC X, it will give you a more enforced error checking. If you miss a block, the machine will recognize that it missed a block. If you accidentally send a block twice, it will throw it out and see that it's a duplicate block. If the checksum is wrong, it will ask for a retransmit. So it's a okay protocol to use. It's more error checking than regular DNC. So let's demonstrate a DNC X program executing. So we'll do a CD, which is change device. We need to be able to send the DNC command both to the machine and to the CompactRIO, so they're both in DNC mode at the same time. So now we'll say DNC X and then hit enter. Now the CompactRIO saw that DNC X command along with the machine. The machine went into its DNC X mode. The CompactRIO just started sending data, and the machine told it, okay, wait, I'm not running yet, so don't send me any more data yet. Now I'll press the start button, and now the CompactRIO is waiting for the machine to say, okay, I need more data, and then when it asks for more data, the CompactRIO will send more data, and then when the machine buffer gets full again, the machine will tell the CompactRIO to stop, and there's this flow control that's happening. Now what you have to be careful of is these lines are indicative of the buffer. The buffer isn't just a couple of lines, it's actually pretty large. But what will happen is you'll see these lines compressed down to just 2 lines if you run out of buffer. That's called data starvation. Data starvation is very bad when you're doing DNC, because then your tool paths will no longer be smooth anymore. And if your tool paths aren't smooth, your cutters get angry, your parts start looking poor. So you have to be very careful that we don't data starve our machine. Now this test was run at 50 inches per minute. So you can see we can easily run 50 inches per minute on an adaptive clearing profile. And that was my goal in this project, and being able to try to run at 50 inches a minute or more. Depending on the adaptive clear profile, I can actually run faster. I've run it up to about 100 inches a minute adaptive clearing, which is pretty good for a machine from 1994. So our DNC file's done, the machine's just waiting, so we can go back into the manual mode. So that's a tour of kind of how I structured this and how I made it work. Again, we don't need a CompactRIO to perform these operations. It's a pretty expensive piece of hardware if you were to just buy one off the shelf for this. I believe an Arduino or a Raspberry Pi or one of the many other embedded devices should be able to do this basic functionality. Let's go down to the office and I'll show you the LabVIEW code that's running inside the CompactRIO and how I structured it and how it works. We're back in the office. Let's review the LabVIEW code that I developed and wrote that's running on that CompactRIO. If you don't know LabVIEW, don't worry. You can still watch this video. You'll still have a basic understanding of the code structure and how it works. LabVIEW is a graphical programming language, so it kind of reads like a schematic, so you'll still get a sense of what's going on. So let's take a look at the code here. This is the top level code that's running on the CompactRIO. Over here we have some initialization items. Now the CompactRIO, in addition to having a standard embedded microcontroller in it, just like any Arduino or Raspberry Pi, it also has FPGA in it. An FPGA stands for Field Programmable Gate Array. And you can think of it as another type of microprocessor, but instead of the microprocessor being set in its configuration, it's actually dynamic. You can design basically a microprocessor in an FPGA, and an FPGA can truly do more than one thing at a time. It's true parallel processing. They're also very fast. I'll explain what I'm doing with the FPGA in here. It's not something that's required for this application. It was just me kind of being cute and trying to see how much throughput I could actually squeeze through this little tiny CompactRIO. So that's what this piece is doing. It's initializing the link to the FPGA. This piece right here is a ini file configuration manager. So we just use a standard ini text file to control our configuration. We basically are just storing some variables in here. If you're familiar with LabVIEW code, this is called a functional global or a action engine. So we take our file, we open our file, and this file is what stores all the standard parameters that we use on PowerUp. the URL of the storage device, the username, password, the temporary folder for local storage, the drive paths, the serial port configuration. I have some stuff in here to help try to format the text output to the machine for the screen width and height so that I try not to wrap the text on the screen. And then we have some timeouts and some retry values for the DNC transfer in case we run into an error. We also have the ability to write this configuration. So if you want to change this configuration, you can send some commands from the machine's console, and the CompactRIO will be able to modify its own ini file and then save the settings. So if you want to change the baud rate or the path or any of those items, you can. So that's all this piece is. It's just basically handling our configuration. The next piece is going to read that file. So this sets the file path, this does the read, and then this creates our temp folder. So in the demo, recall that when we read a file with the CompactRIO, we actually copy the file off of the network attached storage device and keep it locally on the CompactRIO. We did that for two reasons. One, speed, and two, if you're DNCing a large file and you're in the middle of your run and the network goes down or the NAS crashes, you don't want the machine to stop. By keeping a local copy on the CompactRIO, we don't have to worry about the network going down and interrupting our file stream. CompactRIOs are very robust, stable devices. I've never had this thing crash or hiccup. That's exactly why I used it. I did not want to DNC these large files from a PC. PCs tend not to be as stable as a true embedded operating system device is. So after we get the CompactRIO all set, then we open up the serial port. So the first time we open up the serial port, we're going to use 7 data bits, even parity, 1 stop bit. This is a standard serial protocol. After the port's open, we're going to wait for enter command. If you noticed in the example, every time the Fidel machine is in an idle state, the text on the screen says enter next command. So that's the first key off that this CompactRIO is looking for. And the way that we do that is this will see how many bytes are at the serial port, and then this will read out that number of bytes from the read buffer on the serial port. And then we do some searching and scrubbing of any erroneous data. We're looking for carriage returns or line feeds to reset the buffer for the serial, and this is basically just a variable that keeps getting shifted from iteration to iteration. Then it looks for the text enter next command. When it sees a complete line of enter next command without any carriage returns or anything, it knows that the machine is now in an idle state and it's ready to accept the command. Then we transfer to the next state of this simple state machine, which is going to be read command. This is where the CompactRIO monitors what you type on the machine's console, and then will take appropriate action depending on what it sees. If the CompactRIO sees the plus key, and we can change this to use any key on the keyboard, I just use the one directly under the enter key. It's just convenient. You can use any key you want. If it sees a plus key, that signifies to the CompactRIO that, hey, I received the command that I need to then act upon. So it will go through this logic here, and it will end up in execute command. So let's look at that execute command case real quick. The execute command case then takes the serial buffer from what was read off the serial port before the plus key was pushed, and it splits it based on a space. So my command structure is a command mnemonic, space, and then I can have, command variables after that. If we look at the dir command, you'll see the dir command comes in and it executes this case of the case structure. So this is all the valid commands that it can receive. So it'll do the dir command, and then it passes after the space into this guy. This actually performs the network operations. To do my network link to my NAS, National Instruments natively supports WebDAV. WebDAV is just another file transfer method. It's just like FTP, but it's secure. You can use any file transfer or interface system that you want, FTP, WebDAV, maybe a secure shell or localhost. Any of the transfer protocols that are out there, you can conceivably use, as long as your NAS that stores the data and your device that you're using to be your intermediate bridge support whatever protocol you choose. You can use it. In this example, we chose to use WebDAV. So for a directory listing, what we do is we connect to a WebDAV server, then we list out the folders based on this URL, and then this is the directory that you want. This is what's actually searching the listing of directories and seeing if there's anything that matches and if only one matches. If it finds a match and there's only one match, then it will change the path. It will add that path to our directory list, and then it will output to the machine what it changed the path to. If it finds more than one, it will send out an error to the machine, and it will print out text on the machine that says, nope, that directory doesn't exist, or you have multiple matches and you need to define your directory name a little bit more detailed. So that's the dir command. Let's also look at the file command. That's another command that I demonstrated. Very similar. We take the file command and then we pass the arguments into this guy, and he does almost the same things. Here's our WebDAV interface. We're going to list out the file names. We're going to see if we find a file name that matches and that only one matches. And if it does match, what we're going to do is we're going to copy that file from the network location and then move it into the USB folder in the temporary directory. So that's the file command. Then we had the TA-1 command. That's how it actually sent the file to the machine. Again, exact same layout. So this is going to go and make sure that it can find that file again and re-download it, just in case that file may have changed since the first time you loaded it to when you actually send it to the machine. And then after it can verify that that file still exists and is still valid, now it's actually going to send that file to the machine. So that's what this guy does. We have to change our serial port configuration when we're in the manual interface mode. There's no flow control. But when you go to send a file, it uses X on, X off flow control. So that's this piece here. The other piece that we're doing here is this is the file stream manager that I wrote, and it will take the file that you downloaded into a temporary folder location on a CompactRIO, and it will chunk it up into blocks, and then it will send the blocks out the serial port to the machine. As the machine accepts it and does the flow control, it will keep sending the file until the file is complete. So that's the TA-1 send the file command. So all these functions by themselves are actually pretty simple to code. It's just a little bit of network manipulation, a little bit of serial port work, a little bit of string manipulation, and you can get it to go. So there's nothing that's real complex here. It's all basic operations and just stringing them together. Now the DNC transfer function gets a little bit weird. When we go to the read command section, remember we have to put the machine in DNC mode and we have to put the CompactRIO in DNC mode. So this logic down here will look for the command of DNC or DNC X. In our example, we use DNC X. It then looks for a carriage return. So if it sees DNC X carriage return, that's when the CompactRIO transfers over into a DNC X transfer function. So let's take a look at the DNC transfer function. So with this, the serial port needs to be completely reconfigured, so I have to close it. So this closes the serial port, and then we enter into this subroutine here, which is the X modem file transfer. So this little piece of code does very similar things to our file transfer, but it's got a little bit more extra in it. So we still get the same file, we still initialize the file stream manager, and this file stream manager now becomes a little bit more important when we're sending DNC commands. I'm going to go over that in detail when we actually get to the section that sends it. We then reinitialize our serial ports. So for DNC X transfers, it uses 8-bit words instead of 7 with no parity. Because remember, the X modem protocol has a checksum around the entire packet. So rather than using parity detection on a byte-by-byte basis, we're going to use a checksum on a packet detection on the whole entire packet. We then wait for the machine to send the CompactRIO a NAC message. NAC means not acknowledged. When the machine is sitting idle and waiting for data for DNC, it will periodically send out a NAC. Then the CompactRIO can say, okay, the machine is now in DNC mode, it's ready to start receiving the data that I'm going to send it. So it'll drop out of this wait loop, and now it will enter in the main streaming loop. For each iteration of the main streaming loop, we are going to read a block of data out of our data file. X modem uses a 128-byte data packet, so we have to packetize the file in 128-bit packets. And then the last packet we have to pad so that we can say that the file's done. This piece here formats those 128 bytes into the X modem protocol. The X modem protocol will have a header that has a block number associated to it, and that block number is just a counter that increments every single packet you send. That's how the machine can detect both a missing packet and a duplicate packet. A duplicate packet is less concerning because it can just get thrown away and then the machine will send an acknowledge. A missing packet, the machine will send a NAC and then it will error, because we don't want to continue on if we missed an entire packet, especially if that packet contains a tool offset. Then, after it builds the packet, it's going to send it to the serial port. Now this serial port write is a little bit different than a standard write. This is a synchronous serial port write. What it's going to do is it's just going to take that data and send it to the serial port buffer, and then this code is going to return. What that does is it frees up the CompactRIO to then service and get the next data block that's going to be written and get it ready to be sent while the data is being streamed out the serial port. So this is a way that we can multitask and get true parallelism here. By utilizing the serial port hardware, we can let the serial port hardware gate the data out, and then we can do some other stuff while that's happening. After we satisfy and get our next data block, then we're going to see what the acknowledgement was for the previous block. If it's an ACK, we're going to say, okay, the machine acknowledged it, it was a valid packet, we can now send the next packet. If it's a NAC, that is an invalid packet, we need to resend the packet that we just sent and see if we can recover from the error. So that's what this logic does. It either increments the block count or not, and if it doesn't increment, it will resend the last block. After that, we look at the status for our file engine and see if that was the last packet to send. So if it was a successful send and it was the last packet, now we're done, we'll drop out of this loop. We need to send an end of transmission. The end of transmission signifies to the machine that the file is complete and we're done, and then we'll clean up, close the serial port out because we need to reopen it in its previous configuration, and then we'll close our file stream manager. that's basically it when it comes down to what this device has to do and what you would have to code if you wanted to do this yourself, either using a CompactRIO or using another embedded system. Let me talk about this file stream manager a little tiny bit. In order to get the best performance possible out of DNC, you want to remove all of the unnecessary characters. You only have so much time to send data through the RS-232 port. These machines don't support very high baud rates because of their age. If you want to try to increase your DNC speed, you have to get rid of all the unwanted characters and the unnecessary characters. So when you're using DNC, comments are not needed, and they're a waste. If you have comments on every single line of your code, you are just completely bloating out your DNC transfer, and you are not going to get any performance whatsoever out of it. If you have, 6-digit line numbers in front of every line, and N, 10,000 or 100,000, 100,010, 100,020, you are unnecessarily sending characters to the machine that it does not need. DNC does not need line numbers. Some machines may need the line numbers, but for Fidels, it doesn't need the line numbers. It doesn't care about line numbers. So don't send them. So what this data stream manager does is it reads the file from the local storage device, USB in this case, a USB thumb drive. It will read a block of that file. In this case, it's a kilobyte block. It will then send that block to the FPGA, and the FPGA is what's actually doing the processing to remove those, unwanted and unnecessary characters. So let's take a look at this code. So this is just initializing a whole bunch of variables, and this is initializing a big block of data. This down here is initializing the FPGA link, and it's initializing these DMA transfers. DMA stands for Direct Memory Access. It's just a way for two processors to transfer data very quickly without very much overhead. Then we have to initialize the read block. This is where we read the start of the file and preload all of our buffers. So you can see we're doing a little bit of file I/O here, and then we're taking that file I/O and we're putting it into a DMA. After that, it's pretty much just the same thing repeated over and over again. We have a read block function which will fetch any data that's available that the FPGA has already processed and then put it into this data vector that is waiting. If the data vector is full and there's no room left, it will leave the data down on the FPGA and will stop streaming data to the FPGA. If there's room available in the host buffer, it will read to fill up this buffer and keep this buffer full all the time. Then we have a read file. The read file does just that. It sees if there's any space left in the DMA buffer that's going to the FPGA, and then reading that many data bytes out of the file and then sending it to the FPGA for processing. So we just have this data flow from file to FPGA DMA down. The FPGA will process that data and then send it back up through another DMA channel, and then that's when this read block will read out that DMA and then store it locally until we're ready to send that block out, and then this is where it transfers that block out to be sent out the serial port. So we have this nice little data flow set up. The status basically just looks for the end of the file to happen, and then when the end of the file happens, it will send out that the transfer has been complete when all of the data has moved through all the different layers of buffering and DMAs and FIFOs and everything. So we want to make sure we don't lose any data in all of the buffers and FIFOs that we have running. Then we just do a close and we clean up when we're done. So I keep talking about this FPGA. Let's actually look and see what the FPGA is doing. And that is the code inside the FPGA. It's very simple, but the really cool part about it is this loop rate runs at 40 megahertz. That means that with an ASCII file using 8-bit data bytes, we can process 40 megabytes per second of G-code files. So in 1 second we can crunch through 40 megabytes with this FPGA. And it does a character by character filter, which is blazingly fast for what you have to do. If you had to try to do that in a PC, I don't know if you could get that level of performance in a PC. This is the algorithm that I use to scrub the text ASCII data of the G-code file before it gets DNC to the machine. So again, we're looking for line numbers, N and then followed by a number. So if we see that, we want to get rid of that. We're looking for tabs and spaces. G-code doesn't require tabs and spaces. We put them in to make it easier to read for humans, but again, the machine doesn't need it, so don't send it. We're looking for open close parentheses. Those are comments. We don't need to send comments for DNC. So all of these items we're looking for, and if we see them, we basically remove them out of the data stream and stop transferring those bytes up to the return DMA until we see the condition case to then restart transferring the data to the DMA. So in the case for a comment, if we run across open parentheses, we would then terminate sending any following bytes to the DMA until we see a closed parentheses or a carriage return or a line feed. And that would represent either that the comment was closed and then we should resume sending bytes up to the DMA, or if we started a new line, that would reset it and say, okay, you're on a new line, you should start sending that stuff. So that's the logic that we applied to scrub our file. If you're not looking for high performance on DNC, you definitely don't have to do this. This was just a, because we can type of thing, and it did really increase our DNC performance. Like I said, we can do 3D toolpath interpolation for adaptive clearing, upwards of 50 inches a minute on a 1994 machine. So that's pretty impressive for that age of machine. That pretty much sums up the walkthrough on how I did this interface. I hope that provides the level of detail that people were looking for in this interface. If you have any other further questions, please feel free to contact me. Either you can leave a comment in the video, or again send me an email. My email address is in the description of all these videos. I hope this was helpful, and thanks for watching. We'll see you on the next video.